Okay, so we're looking at inscribed angles. The first one we looked at, we start with central angles. This would be a central angle right here, the 108.4 degrees approximately. That matches up to this arc out here being the same measurement. So whenever we move them, that measurement of this central angle being on the center matches to that arc. The inscribed was the new one today. Inscribed is half of the arc. It's also half of the angle. It is always going to be half. Okay? This is a key mistake that happens when you start seeing the mix of all the problems and all the different segments and chords and angles and arcs show up. We forget that to get to the inscribed, it's half of the arc and half of the central angle. Think of it like a slingshot. As you pull it further back, the angle gets smaller and smaller. Whereas this is 86, this would be 43. If I kept going further back, that angle gets smaller and smaller and smaller. As I go, we got to take half. Opposite of that, you're going to double to get to the values. Okay? Your first corollary said as long as they go to the same arc, the angles are congruent. So if I take this point and move it around the circle, what's going to happen to the angle measurement? It stays the same because it goes to the same arc. That arc is still 86.45 degrees because it's the same as this angle. So when I move this, it matches to it. It's always going to be the same. So whether it goes to the arc from here or over here, it's always the same. Now, I know what you're thinking. Oh, you said it, so it doesn't change. No, look, it does change. Okay, we can adjust the arc, but then this value stays the same. Okay? Now, we kind of denied the fact that angles are bigger than 180 anymore. We're kind of forgetting that trig fact happened. But if you had an inscribed angle that opened up to a major arc, it would still be half of it. We had the 96 degrees because that's half of the 192. You're not going to see that too much, but it does work as well. Okay? Now, over here, this is when we've taken that inscribed angle and we've moved it so it's so far that the line is now a tangent. And that would happen when these 2 points would meet. And it looks something like this. Now these work the same way because in the big circle, it's major arc, minor arc. It's 2 parts. That's still totaling to be 360. Down here, these are totaling to be 180. So you take half of the arc to get to the value. So let's see if I can get a little closer value here. So this arc is about how much? The minor arc. Approximately. Nearest whole number. If the angle is 60, what's the arc? Yeah, it'd be 120 right here. If that's 120, what's the rest of it? What's the major arc? 240 because we know the 120 from 360 leaves you with 240, or you double 120 to get to 240. And this works anywhere because you have the supplementary angles at the intersection, and then you have the arcs adding up to 360. Okay, and we'll go, what did I just hit? There we go. Okay, I have a triangle, inscribed triangle. You have a few on there where you need to go to the arcs. You can just double the values to get, let's say, this arc out here. I would double 57. To get to that, down here I double 73, double 50, 49.9 to get to those values. Not the reason I'm here. Which corollary are we going to look at? Was there any corollaries with triangles? Which was? Oh, okay, so we move this triangle around so the diameter and the longest side, or really the side, goes to the center. And what happens to the triangle? It becomes a right triangle, which is this angle right here. That is close enough for what we need. Okay? Wherever it moves, it's still going to be 90 degrees. Now, it opens up to half the circle, a semicircle, which is 180. And that goes back to when I was moving it earlier. But look for that hypotenuse diameter, right triangle. If I wanted this arc, I would double the 62. If I wanted this arc, I would double the 27. And you can go through and solve those as well. But that hypotenuse diameter, we need to think right triangle. Can I get exactly? Maybe. No. All right. This one. Okay, it is not in quadrilateral that opposite angles are congruent. The opposite angles are supplementary. Now, what I tried to explain in that was saying, let's look at the 105 and the 74. Together, those both go to arcs that make up the whole circle. So from the whole circle being 360, if we take half of them, you're left with 180, which guarantees it's going to be supplementary. Both of these arcs cover all the circle. So they will have to be supplementary. Then we look at the other set, the 90.59 and the 89.41, which are actually pretty close to each other. Those will also add up and be supplementary. Now, this is tough because we've seen opposite angles before. Opposite angles we've seen before are congruent because those are in what shape? Yeah, that's in a parallelogram. So, got to be careful. Opposite angles supplementary because we have the full circle's 360. We take half the 360 to get to it. Speaking of quadrilaterals, what type could we make? Could we make a rectangle?
No. Wait. No.
Yes. Let's go with yes.
No.
That's pretty close.
Good enough.
Yeah, that's pretty close. We could make a rectangle. If we could make a rectangle, could we make a square? Yeah, rectangle and square, all right angles. Right angles are supplementary. So that would work. How about a regular parallelogram, not a rectangle? Okay, opposite angles are congruent in that case. We want congruent and supplementary, so that's not going to work. Another one you could make is a trapezoid. Something like that's pretty close. You can make a trapezoid if you need to, and that goes back to the opposite angles being supplementary. So those are the different rules you have for that section. Where we start to go is we're solving for angles using these different properties together. So they all kind of keep building